third lecture, we shall now continue the investigations of a punctured metric cone that we started in lecture 2. So remember, we were considering an n-dimensional Riemannian manifold, Xn. Gx is the metric. The manifold is supposed to be closed and oriented, as always. And then we had associated to it what we called the punctured metric cone. And it's, as the name says, equipped with a metric as follows. You take dr squared plus r squared gx. So that's what we call the punctured metric cone. The cone is open, but punctured means that also the cone point itself is removed, so that topologically the punctured metric cone just looks like an open interval 0, 1 cross x. And the coordinate on 0, 1 we called r, and I'll use x1 through xn for the coordinates on x. And we will consider the projection pi to x from this punctured metric cone. And we defined the L2 cohomology based on smooth forms. And in particular, this cohomology is then defined for this punctured metric cone. And our goal was to understand this cohomology group better. So I will not discuss all the details of computing this, but I want to give you an overview of how it goes in principle. Okay. So this map, pi, induces a map pi star pullback of differential forms. And the first claim I want to make, claim 1, is that in a certain range, this pullback map restricts to a map of L2 forms. Okay, so if I is less than or equal n over 2, I claim, then pi star restricts to a map from I forms on X. So I could put a 2 here if I wanted to, but it's the same thing since X is compact. 2 L2 forms on the punctured metric cone. So let's prove the claim. So the explanation here is so in evaluating the integral, we'll have to think about two things. We'll have to think about the volume form, and we'll have to think about the norm of such a pullback. Now, a little calculation shows that if you pull this form back and consider the norm squared on PMC with respect to the PMC metric, then this is at a point Rx given by 1 over r to the 2I omega, and this is the norm on x squared. So that's one thing that we'll use. And as for the volume form, you see, so in Jochen's talks, we emphasized LONFs, right, local orthonormal frames, and in fact, then in terms of a LUNF, an oriented local orthonormal form, frame, we can then express the volume form simply as a wedge product of these covectors, E upper 1 through E upper n, right? But of course, if you, on the other hand, express the volume form in terms of coordinates, then so expressing the metric on PMC in terms of coordinates, you get components Gi, J, let's call them, and then you have to look at the determinant. Now, of course, if you look at this metric, there will be n rows coming from this, each of which is multiplied by r squared. So the determinant then gets multiplied by r to the 2n times the determinant of gx. And so therefore, if you take the square root, this goes away, and it looks like this. And the square root, if you write the volume form in coordinates, it's precisely this times dx1 wedge and so on dxn. And therefore, the volume form on PMC is in fact r to the n dr wedge volume form on X. So now using this in our calculation, we say, okay, what is the integral of the norm of the pullback? Well, so I integrate really over an interval cross X, and if I plug in what we have up here, then I get an expression like this. But since omega, of course, is a form on X, it doesn't depend on R at all. So I can separate out these integrals into an integral with respect to R, and then times an integral over X, like this. But I know, of course, that this is finite because X is compact, right? So therefore, this integral then is finite precisely when, well, either omega is 0, remember omega is smooth here, or otherwise you must have r minus 2I greater or equal to 0. And that's exactly what I've provided for. I've exactly provided for this condition, and therefore, if we are in that range, in fact, the claim is established. Okay, so we have a good map. Now, of course, pi star as a pullback map, it of course commutes with D, and therefore you certainly get a map on cohomology, and this map I want to study next. So from HIX to the L2 cohomology of the punctured metric cone. So claim 2 is then this map here, this pi star, is an isomorphism, well, in the range where we have it. So again, for I less than or equal n over 2. Okay, so to see this, we shall construct a certain homotopy operator. So in order to prove claim 2, we shall introduce a certain homotopy operator K. And as you probably know, a homotopy operator in terms of the degree shift always goes opposite to the boundary or co-boundary map. So in a chain complex it goes up, and in a co-chain complex it goes one down. So the D is raising degree by 1, so the homotopy operator has to take an I form to an I minus 1 form. Right, so we construct a map of that type. So to do this, let's suppose I have a form on the punctured metric cone. So suppose omega is now a form on the punctured metric cone. Then write it as alpha plus dr wedge beta, where alpha and beta do not contain dr. So alpha is an I form also, but notice that beta is an I minus 1 form. Right? This is an I form, this is an I minus 1 form. And so in fact, if you write it in coordinates, alpha will take the form sum over I tuples capital I, alpha I Rx dx I, and similarly beta will take the form sum over I minus 1 tuples j, beta j Rx dxj. No dr, right? So we can write the form like this. Then to define k, you integrate the beta j's. So you integrate these dr. So where do you integrate? So before we do that, we say fix, say an R0 in the open interval 0, 1. Somewhere, it doesn't matter where. Now once we fixed it, I integrate from R0 to R. And I take this as my coefficient functions. And this is my definition of k omega. Okay. So notice that k omega is an I minus 1 form. So I certainly get this way a map from omega I PMC to omega I minus 1 PMC. And this construction has two main properties. And my suggestion is actually that you think about those for the problem session. So I've told you exactly, everything you need to know. The operator is there. And so in the problem session, I suggest that you show that dk plus kd of omega is equal to omega minus, and here's the trick now, right? So it's a homotopy operator between what, right? It's a homotopy operator between the identity and, of course, something that's supposed to come from here, right? That's the trick. We want to, for example, to show that this is surjective, you need to produce a form here that up to an exact form maps to this. So that's exactly achieved by this, because it's a homotopy. This is the difference between omega minus pi star of, and what you have is alpha at R0, right? And if you fix the R0, alpha at R0, that's a form on X. Right? And so this is good, right? This is, and secondly, of course, and the second key property that you need for the K is that if now omega is in fact an L2 form, then K of omega is also an L2 form. And so this requires a little estimate similar to the estimate that I've done here. So I suggest that you try to do this on your own for the problem session. So granted this, I can then go ahead now and try and show that this is an isomorphism. So for example, why is pi star surjective? Okay, if omega represents a class in the L2 cohomology of the punctured metric cone, so that in fact it's a closed form, well then according to 1, I can write it as dk omega plus kd omega plus pi star of alpha r naught. But this is 0 because the form is closed, and therefore it is a pullback of something coming from X up to an exact form. And this shows that the map is surjective. Now, yeah.
Yes, something. I mean, you assume that each class in H2 can be represented by an element in L in omega 2 without parentheses, right?
Right.
A smooth L2 form.
Right. Right. So the important thing is that, yeah, so here property 2 is used. Property 2 is used. I need to know that this is L2, of course. And this is and smooth, right. And smooth. But this certainly is smooth, right? I mean, since beta is smooth, this will be smooth.
Well, I mean, there was this difference between 2 in parentheses and 2 without.
The difference was that for the 2 in parentheses, also the derivative, the exterior derivative has to be L2. And we only use smooth L2 forms and not the L2 closure.
Yeah, this is what I wanted to say. Because the class contains everything.
I mean, here at this point, I don't need to. I mean, here I start with a form that's in there, so I know the conditions, and I just need to produce something in X where there are no conditions at all of an L2 type. So now, and then on the other hand, why is pi star injective? Okay, so here I start with a form omega. Let me actually, it's better to call it alpha. A form alpha representing an element in here. And so it's a closed form. And pi star of alpha as a class here is 0. So I know that this is d of some eta, where eta is an L2 I minus 1 form on the punctured metric cone. And I need to show that alpha is exact, on X. Right? So why is that? So if I use the homotopy operator on eta, I know that eta is equal to dk eta plus kd eta plus pi star of something. Now let's say I write eta as say gamma plus dr wedge delta, then I can say this is gamma at R0. So d of eta, well, d squared is 0, so this term goes away. So I have this. Plus d of pi star gamma R naught. So what about this term here? K d eta. Well, d eta is pi star alpha. So this is k of pi star alpha. But if I pull a form back, if I know that a form omega does come as a pullback of something from X, well then clearly the beta is 0 because there is no dr component, right? So I know here that for this the beta is 0, and that's why I wrote it as alpha, right? But then by definition this operator is 0 because you would integrate in this formula, these beta j are all 0. So you integrate 0, so k is 0. Therefore, I see pi star alpha is equal to d eta, and this is equal to well, now this term also goes away, so the only thing that remains is this one. So it's d of pi star of gamma R0. And this commutes, so I can take pi star outside. So it's pi star of d gamma R0, which of course implies that alpha itself is equal to d of gamma R0, and so I've succeeded now in showing that alpha is exact and therefore 0 in the cohomology of X, and the map is injective, and so hence the map, this establishes claim 2, right? So we've computed the L2 cohomology in that range. Now the other range is somewhat similar in principle, but technically much more involved, and I won't say much about it. I mean, I'll just say what an idea would be, but you can't get away very well with just using smooth techniques. So let me say a few words about now a third claim, namely that in the other degrees, if I is greater than n over 2. So the claim would be, in principle, that these groups vanish in that degree. Now, the idea here would be as follows. Try to set, we again define a homotopy operator. Try to set k of omega equal integral from 0 to r beta, just as we did before. if this works, right? So then, if this works, then try to show, well, then it would show, right? If you actually knew that this integral existed, you could then readily show that kd plus dk of omega is equal to omega. And so now if you have a class, a cohomology class here, so that this is a closed form, then omega is equal to, since you lose that term, what's left is this, and so omega would be exact, and therefore 0 in cohomology. So what one has to see is that this integral exists, and this I won't discuss any further. I mean, what you have to do is essentially you should look at an integral, of course. Maybe from R1 to R2 and then x, and try to estimate that. Sorry, you look at this. You don't look at the norm squared, you look at this. And so maybe what you want to do is use Cauchy-Schwarz. So maybe you want to, in fact, use Cauchy-Schwarz inequality, where you put in some power of r, right? And then you get a product of two terms, one of which involves the norm of beta x squared, and you see that that's finite because, after all, you start with a form that is known to lie in here. So that piece will be finite. And then you have another piece where you have r sort of with the opposite power, and then the range comes in to see that that's finite also, right? The opposite power that you get from the application of Cauchy-Schwarz, that will then be seen to be finite roughly. I mean, that's sort of the idea because you're in that range. And then you see that this integral is finite, and you argue that therefore this integral at least exists for almost all x and so forth and so on. But I won't go into it. I mean, that's the basic idea. Okay, so the summary is then, the summary here that you should remember from this, yeah.
In this formula for KD plus dK, why does there not appear such a pi star alpha as in the above case?
Here I'm integrating from 0, because I'm integrating from 0, whereas previously I integrated from a fixed R0, which lies somewhere in the middle of this interval. But here I actually go to 0. That's the difference. So no such term appears in the formula for the homotopy operator. So the summary then is the following. The L2 cohomology of a punctured metric cone on a space X is Hi of X when I is less than or equal n over 2, and it's 0 otherwise. Now I'll say this is the same as, you should compare this now to the calculation that I made yesterday for the intersection homology. Well, I did it in detail for infinite chains. You want to compare this to intersection homology with finite chains with respect to a middle perversity. And then you'll find that it's exactly the same. And as I said, Cheeger and Goreski-McPherson, on the other hand, they were working independently. And I believe it was Sullivan who knew both results and saw this comparison and conjectured that these should maybe be theories that are closely related, or in fact, maybe one is the dual of the other, isomorphic to the dual of the other. And in fact, let me go a little bit further. This was just consideration of a cone. But what Cheeger then does is, suppose Xn now is a PL pseudomanifold, and in fact, maybe even with a fixed triangulation. Then Cheeger says, cover it by what he calls handles, Riemannian handles, Uj. So these are open subsets, but they have a special form. And in fact, we assume that X minus the singular set, so sigma stands for the singular set here. X minus the singular set. This has a metric, this is Riemannian. So you cut out the singular. So this is much like what we did with the punctured metric cone, because there we cut out the cone point, and the cone point is the sigma in the case of a cone, right? And now we cut out all of sigma in general for a general pseudomanifold, and we equip it with a metric. But the metric is special. We want to assume so that X can be written as a union of Uj, and the Uj are, and now I'll say in a second what the symbol here means, they should look like 0, 1, n minus j cross an open cone on links, right, as usual, of dimension then j minus 1. So in other words, if you remove the sigma, it should look like the punctured metric cone, because then removing sigma and intersecting, right, removing sigma from Uj means you remove the cone point here in this factor, right? So you take this, the punctured metric cone on the link, and then I want this to be a piecewise smooth quasi-isometry, where this is equipped, of course, with a metric that we discussed earlier, and this is equipped with a standard metric. And then it should be, these pieces should be quasi-isometric to this. So this is what Cheeger calls Riemannian handles, right? He calls these are called Riemannian handles. Well, there is a constant, up to a constant, right? It's sandwiched between like this, right? That's what it means, quasi-isometric. So, I'm sorry?
This preserves the L2 commodity.
Right. Yeah. That's also, I remarked this yesterday, that the H2 homology is sensitive to the metric, but only up to quasi-isometry. Right. Okay, so now we need one further notion. A Riemannian handle such as these is called admissible in the language of Cheeger. If, well, either J is even, or, so let's see, if J is even, you see, then J minus 1 is odd, so the link is odd dimensional, so there isn't a middle dimension. But in the other case, where J is odd, J minus 1 is even, so this is an even dimensional space, so it has a middle dimension that you can look at, and you look at the middle dimensional L2 cohomology. And then, for such cases where J is odd, you require this to vanish. And this now later has been called a Witt condition. And I'll return to Witt spaces from another point of view later in this course. So this is called a Witt condition. So the middle cohomology of links, L2 cohomology of links, should vanish. If you translate this to intersection homology, you would say the middle intersection homology should vanish for links of even dimension. So let's call this admissible. So now the theorem, so Cheeger, it's really two theorems that I want to mention here, both due to Cheeger, are so the assumptions are let Xn be a PL pseudomanifold assumed to be admissible. So then you look at you compare the L2 cohomology of X. Well, I should really write, I mean, what has a metric is X minus sigma. So we should really write the L2 cohomology of, and this is a manifold, right? X minus sigma is a manifold. But the singularity structure is not lost to this. It is remembered by the metric. So that's what you should really understand. In principle, topologically, we are now throwing everything away, right? We cut out the singular set. What remains is the top stratum, and we calculate something on the top stratum. So you might be worried. But what remembers the singularity structure is through these handles, the metric here, right? And that metric remembers the singularity structure. So that's very important here to realize. And so the notation is often that one then defines H2 of X to be H2 of this. But maybe I'll write it like this. Okay, so this is then isomorphic to Hom of intersection homology with the middle perversity. It doesn't matter which one you take. One can show because of that condition, because of the admissibility condition. This is somewhat of a subtle point, but I will explain this better as the course goes on. But of X with real coefficients now are where you essentially you do the usual thing, which was explained yesterday by Jochen. You take a form, an L2 form, and you map it to the linear map which sends an intersection chain to an integral, to the integral of omega over that chain. And this is defined, this integral is defined for enough, I'll say, for enough intersection chains, Xi, so that this makes sense. So that this makes sense. I mean, there is something to do here. It's not right, but in principle, the isomorphism is given by that map, as it is in just for smooth manifolds, if there are no singularities present. So that's one theorem, and the other. So really, they are computable in terms of each other, right? But you have to use the middle perversity. That's very important, right? You take the middle one. Secondly, Poincare duality, right? And it can also be phrased in the simplest possible way here. I mentioned this at the very beginning on Monday in my first lecture, that if you want to do Poincare duality, if you want to see it in the de Rham picture, you take the wedge product of two forms and you integrate, and you do exactly the same thing here. So you go to the complementary dimension, L2 cohomology, and you create an intersection form, if you will, by taking a form omega and a form eta and integrating over the manifold x minus sigma the wedge product of the two forms. And the statement is this is non-degenerate. So this is what Cheeger proves. And the basic thing to understand in all of this is the calculation that I indicated here on the cone. Because then you prove, what you have to also prove is a Mayer-Vietoris principle. After all, if this has a Mayer-Vietoris principle and this is supposed to be isomorphic, then this should satisfy a Mayer-Vietoris principle also. So you try to prove it directly, and once you have it, you can just use the calculation of the cone together with the Mayer-Vietoris principle and a 5-lemma argument, as usual, to get this statement of Poincare duality. So that's in principle the program of the proof that Cheeger carries out.
Do we assume more on the pseudo-manifold? Because what you explained first, we know how to handle punctured metric cones on manifolds, but the links do not have to be manifolds in general.
Well, of course, you cut out the singular set from the link also. I mean, if you cut out the entire singular set, then it is in particular cut out from all links, right?
Okay.
And so it works.
So it's in principle there the punctured metric cone of the links minus the singularities.
Yes, okay, yeah, right. So more precisely, maybe, no, I don't like this. I mean, actually, I really want it like this. I mean, because the puncture, it already tells you that you have to view it this way. The word P, the letter P means that you should cut the singular things out, okay? Because that's what's, right? The P is responsible for cutting away everything that the singular points themselves. So that is my interpretation here, let's say, okay? So that's right, yeah.
So just taking the top pure stratum.
Right, yes, right, exactly.
This is what you do inductively.
Right, exactly. Okay, so maybe I'll leave it with that for now. And I promised that I would discuss a third approach. To Poincare duality, on singular spaces. And so we've discussed many aspects of two theories that work very well, intersection homology and L2 cohomology. But of course, as always, there are some disadvantages as well to any given method, and we haven't looked at those at all. So intersection homology and L2 cohomology have certain disadvantages, such as, for instance, the following. By the way, I didn't explicitly emphasize this, but you can, of course, not just define intersection homology, but you can define intersection cohomology as well by doing the usual thing. You look at hom of the chain complex, and then you take the cohomology of that, right? And that you call intersection cohomology. So we may very well talk about intersection cohomology also. Though in order to do that, you want to use finite chains. When you apply hom and create an intersection co-chain complex, you want to use finite chains. That's really what you should do. So what are some disadvantages? Well, let's do an example, maybe. Suppose I have a 6-dimensional pseudomanifold, and I have a class alpha in IH2, say with the middle perversity always. Sometimes, by the way, if I don't write a perversity, then I will mean the middle one if there is a uniquely defined middle one. So here I'm supposing, let's say X has only one isolated singularity. So it is of the form M union along the boundary cone on boundary M. So suppose we're in that simple situation. So this is a 6-manifold, let's say. Now, suppose I take a 2-dimensional cocycle, intersection cocycle, and I would like to form a cup product, say with itself, right? Suppose there existed a general cup product on intersection cohomology. So in particular, then I would also get squares like this. This is of course connected with the problem of finding squaring operations in intersection cohomology, etc. But suppose I wanted this. I would like to have this. This should then lie in H4. So the question is, can I do this? Does this in general exist? But you see there's a problem with having this, because dually, you know, the cup product is of course supposed to be represented under duality by the intersection form, right? So you could look at duals, and then you take the intersection product. This is the intersection product. But now this lies in, but alpha hat lies in IH4 homology. And so this should lie in IH2. Right, according to the intersection form, the Lefschetz type intersection form of Goreski-McPherson that I wrote down yesterday. So it should lie in IH2. But suppose that this is a cycle that can't be moved away from the cone point. Right? This is above the middle dimension. 4 is bigger than 3. So alpha hat is allowed to go through the cone point, And we've certainly seen examples of cycles that cannot be moved off the cone point. Some of them really are forced to go through it in here, and you cannot make a homology through intersection chains to move it off the cone point. So suppose it has to go through it. Then for the intersection, that chain also has to go through the cone point. You cannot move that away from the cone point either. But it's a two-dimensional chain, and since that's below the middle, the chain is prohibited from going through the cone point. So it can never work. This proves that you cannot in any way make intersection cohomology into a ring. Okay? Okay. So the conclusion is we deduce from this intersection cohomology for a fixed perversity cannot be made into a ring contrary to ordinary cohomology. So there is no cup product. There's no possibility ever of defining a reasonable cup product. In general, I mean. So this is kind of a serious problem, of course, because lots of results in algebraic topology on manifolds rely on the ring structure of cohomology. So of course you can define a cup product if you allow the perversity to change. Of course, since in the intersection product the perversity changes, as we have discussed in the earlier lectures, therefore, of course, you can define a cup product if you change the perversity from this one to another one here, right? That's clear. That can be done. So there's no contradiction. There are some papers in the literature where cup products on intersection cohomology are discussed, but you should notice that all of these papers change the perversity. So it's not really internally a ring structure, right? It takes you outside of the group into a different group, so the perversity degenerates more and more the more products you take. So it gets, in a sense, weaker and weaker, and it's kind of it's not very useful in practice. I mean, it can be applied in certain situations, but it's not a ring. It's not a ring as such. And similarly, you can make such arguments, of course, since we have this isomorphism, you can similarly make arguments like that also on this side, because notice that in the L2 picture, the product of two L2 forms need not be L2. And so also from that point of view, you see that you cannot, using the wedge product, endow the L2 cohomology with a ring structure either. I mean, that's of course already suggested by this isomorphism. If you could, there would be something wrong in that theorem, right? Of course. So those are serious disadvantages, but there are others. This is one disadvantage, right? So the disadvantage one is that there is no DGA structure on the underlying complexes. But there is a second set of questions or problems that one could ask, namely the following. And this is an old question. How to define generalized intersection homology theories or cohomology theories. So you see in algebraic topology, well, first you learn about ordinary homology. So I mean now finite chains, of course. Something that satisfies the Eilenberg-Steenrod axioms, right? So that you learn first. But as you go on in algebraic topology, there is a vast generalization of this called generalized homology theories, where you give yourself what's called a spectrum in the sense of homotopy theory, of course. E is now a spectrum in the sense of homotopy theory, and every spectrum defines what's called a generalized homology theory. Also, of course, generalized cohomology theories. And there are many extremely important examples of this, such as, for example, K-theory or Bordism theory, and many others that have been studied, right? So you can generalize in that manner. But the process that we looked at changes homology to intersection homology in order to restore Poincare duality in the presence of singularities. So how do you close up that square? Right? What goes here? In other words, is there a version, if I give myself a spectrum or at least a certain theory like Bordism or K-theory, so that I could then define I E star with some perversity of a space X, right? So this is an old and very important question, which is very hard to answer. And it's hard to answer for the following reason. It's hard to answer for the following reason. There is an old theorem due to Burdick, Connor, and Floyd, which says that if such a generalized homology theory satisfying the Eilenberg-Steenrod axioms, which is not, of course, literally true for intersection homology, but suppose we have such a theory here, some homology theory, if this theory comes from a chain functor then E star is trivial. Meaning that, so what does trivial mean? Trivial here means is in the sense of homology theories. So you call a homology theory trivial if the Atiyah-Hirzebruch spectral sequence sort of collapses and it looks like the E2 term of that spectral sequence, right? So in other words, if this looks like some P plus Q equal N ordinary homology, P X E Q of a point, right? So then you call it trivial. I mean, you can always define a new homology theory by writing something like this down, if you like, right? But these homology theories, they are not very interesting, right, from the topological point of view, because they essentially record the same information as ordinary homology. So they are really not very interesting. So, for example, K-theory and Bordism are not trivial in that sense. I mean, K-theory is not trivial. But you see, so I'm not deriving a formal contradiction. All I'm saying is that your cards are not very good. If you want to solve this problem, your cards are not directly very good if you use what we have done earlier in this course, right? Then your cards at least are not very good. Yeah, because intersection homology is just defined in terms of chains, right? It comes from a chain theoretic description. It comes from a chain theoretic description, and therefore, if you want to do something like, if you want to define intersection K theory, and you try to do this through some chain complex, then in light of the theorem of Burdick, Connor, and Floyd, this may not work very well, right? This may not work very well, because chain complexes are sort of too weak to express K theory. Chain functors are too weak to express K theory, right? According to that theorem. So what to do, right? So it's a very difficult old problem. What is intersection K theory? But here's an idea. And this brings us now to the third approach to Poincare duality on singular spaces. All of these problems and disadvantages that I've now outlined could be solved by simply doing the following, by specifying the approach. So this is always a good idea in topology. You try to specify as much as possible because spaces have an incredible amount of information in them, hidden, which is not visible on chains alone, for example, right? The spaces have an incredible amount of information buried in them. So the idea is specify this. And so more precisely, the idea would be if you have a pseudomanifold X, you try to associate to it by some homotopy theoretic process not a chain complex, but something much more powerful, a space, right? A space which I'll write as IPX, where P is again a perversity function, as in intersection homology. But this will be a space, more precisely a CW complex, a cell complex, such that, so what do we want from this space? Such that there is a non-degenerate intersection pairing. So you can take, of course, the ordinary homology of that space now. And suppose we use real coefficients. Right? And then there should be a pairing between Hi and Hn minus I, ordinary homology, for the IQ space of X, intersection space. So these are called intersection spaces. So that I have a pairing to R, non-degenerate. And here, of course, P and Q are dual. Notice that the duality statement, the theorem of Goreski-McPherson, also just refers to real or rational coefficients, right? It doesn't hold integrally. We didn't say anything about integral intersection homology, and we don't say anything about integral homology of these spaces either. Right? That's a little bit too much to ask. And to discuss integral duality, I mean, one could do that, but it's much more, I mean, it's somewhat more involved. There's more that one has to say if one wants integral duality. Now, suppose one can find such an intersection space, then notice that it solves all of these problems at once, right? Because this solves the above problems 1 and 2, because it is clearly now a DGA, right? I mean, if you take the ordinary cohomology of that space, well, the cohomology of any space whatsoever is always a ring. In particular, this one is a ring. So that solves problem number 1. Is a ring under the ordinary cup product. Also, of course, since it's the cohomology of some space, it's automatic. One doesn't even have to say anything about it, that there are cohomology operations, Steenrod squares, etc. So it has a fairly rich algebraic structure. By the way, I will call this HI star P of X sometimes. So, I mean, there are two things here. There's the spacification process. You could be interested in the space itself, but on a slightly weaker level, you could be mostly interested in the cohomology of that space. And so in particular, this gives you a new cohomology theory for singular spaces that satisfies Poincare duality also. Right? But since we know this, we can of course immediately deduce from this that HI, right, that this theory, I could do this with homology also of course, is not isomorphic to IH in general. Because one, we've just observed intersection homology, IH cannot be made into a ring, but this one can, and therefore it follows that they are not isomorphic, contrary to these two theories, which are dual to each other, right? They have similar properties. They are constructed in completely different ways, but their properties are entirely the same because of that isomorphism. But this third approach leads to a different theory, which is neither isomorphic to intersection homology, nor, because of that theorem, to L2 cohomology, at least with Cheeger's metric. And it's in fact a current research project to find metrics on X minus sigma so that this new theory can be described as an L2 cohomology group with respect to a different kind of metric. And you have to use what's called the scattering metric. So it seems to go in this direction. One has to use the scattering metric and forms associated to that metric rather than the conical metric that Cheeger considers. Okay, but the second problem is also solved because you could simply set, for example, I mean, there is now a Ki theory obtained simply as a kind of an intersection K theory, although the analogy is not perfect because, of course, HI is not isomorphic to IH. But you could form such a K theory which takes the singularity structure into account and satisfies Poincare duality by simply taking the K theory of the space IPX. And so since I'm not going through a chain complex but have a space, I can do this now, right? So it's much more powerful. But because of all that additional structure that's not present in intersection homology, it is therefore to be expected that these spaces are not so easy to form, and in fact, they cannot exist for any pseudomanifold. A big advantage of intersection homology is certainly that it's very generally definable. In fact, later, in one of the next lectures, we will see that using sheaf theory, all you need basically is a filtration of the space to define intersection homology. So it's very generally defined. but has somewhat weak algebraic properties, whereas this theory has much stronger properties, algebraic properties, but does not exist for every pseudomanifold. So this leads to very interesting questions that are subject of current research projects. Which pseudomanifolds exactly do allow for the existence of an intersection space? I won't be able to go much into this in this course, but I want to indicate how to do this, at least when you have an isolated singularity. So if you have isolated, I mean, this is what we mostly talked about anyway. We investigated these cones in detail and so on, and spaces with isolated singularities. So at least one should try to understand this in those cases as well. So the construction of these spaces for X, a space with for X a space with one isolated singularity, that is to say, it is of that form topologically. So boundary M here is then the link of the singular point. So what do you do? We need to recall from homotopy theory the concept of a Moore approximation. So definition, a Moore approximation of level k, where k is some integer, maybe a non-negative integer, doesn't matter. A Moore approximation of level k of L, of a space L, is such as this link here, is a space which I'll write L less k together with a structural map, let's call it F, from L less k to L such that, well, first of all, the homology Hi, and now again, I'm always talking about ordinary homology now. In fact, it's best to imagine cellular homology and CW complexes for all of this. The ordinary homology of L less k is 0 when I is greater or equal to k, and in the other range of degrees, the map F induces an isomorphism. So, and F star Hi L less k to Hi of L is an isomorphism when I is less than k. So this is a spatial homology truncation, right? It preserves, you try to find a space which preserves the homology of L below k and otherwise truncates it cleanly above k and in degree k. So that's called a Moore approximation in homotopy theory. And so the fact is these exist. These exist for CW complexes L. So it's no problem to get these. Okay, now using such a Moore approximation, we can form the following composition. I go with F into L, which is the boundary of M, and the boundary of M includes into M in a natural way. And let me call this composition G, and then the intersection space for perversity P is by definition the mapping cone, that you're familiar with in algebraic topology of G. What I owe you still is the exact relationship between P and N and K, right? What is the relation between P and K? So where you take K to be N minus 1 minus P of N. So that's how the perversity comes in the dimension. Computing, given the dimension and the perversity, you get a K, and that's where you form the Moore approximation. And then you get this CW complex IPX, and then you can prove, in fact, then this becomes a theorem, right? And then this is in fact true, as one can show. So that's a theorem then. Perhaps it's good to do an example here. And we'll do more examples in the problem session. But let me carry out an example to show you how it works. We look at a curve, basically at elliptic curves, and then we let them degenerate. So I want to look at the curve y squared equals x times x minus 1 times x minus s. I look at this in CP2. This is a curve x, but it depends on a parameter s. So s here is a complex parameter, let's say less than 1. So when s is not 0, xs is a smooth curve, a smooth elliptic curve. So topologically, it looks like this, right? Like a T2. But when s goes to 0, and then when s becomes 0, it degenerates. So then you get x squared times x minus 1. So it's what's called a node in singularity theory, in algebraic singularity theory, right? A singular point develops, it's called a node, and topologically, this looks like a pinch torus, and that's why, I mean, this is an example that we're already quite familiar with, because we've discussed it at length in the last problem session. So you see the pinch torus coming up. And we are already familiar with the ordinary homology, H1, and so this is x0. Sometimes for x0, I will also simply write x. This is the guy that actually interests me because that's the singular space. So H1 of x0, we have seen in the problem session is just z, and the intersection homology in dimension 1 of this guy is 0, we have also seen. But this is somewhat peculiar, right? Somehow this is not so nice because you have the feeling geometrically that there are still cycles that are also cycles present in this space for which Poincare duality makes perfect sense. I mean, you still have this circle here. This color. You can look at this circle, the meridian, and you have the longitude, and they are perfectly dual to each other. There's a there should be a perfectly nice intersection product definable, but somehow intersection homology cannot see this. So let's contrast this now with this new theory HI. So what would be the intersection space of X0, of this pinch torus? So the intersection space of this X0. Well, according to what I said here, first I must find L less 1. But what is L? So L here, well, the link consists of two circles. It's a disjoint union of two circles. So if I have to truncate away the first homology of a circle, I just use a point, right? The one skeleton, if you imagine this as a cell complex, you take, right, the minimal cell structure is you take 1 0 cell and 1 1 cell. If you want to find a Moore approximation, L less than 1, you simply take away the 1 cell, the 0 cell remains. So it consists of 2 points. And then you take, so what is M here? M is what you obtain when you remove the cone from the space. So, looks like this. Now we attach to this M, according to the definition, we attach the cone on this, but so here you see these 2 points in these 2 circles. This is the Moore approximation, and then you cone these off, right? That's what the mapping cone says. So you cone this off. Here would be the cone point of that mapping cone, but in other words, you just join. What happens here in this example then is that you just join these 2 points by an arc. And that would be the intersection space. So sorry, this is not M anymore now. This is now the intersection space. So I leave it to you to determine for which perversity this happens now and so on. I mean, the K that you need is 1, right? The K that you use is 1 here. So what is the of course, that space is really homotopy equivalent to a wedge of 2 circles. And so you immediately know what the first homology is. So what is HI 1 of X0? Well, it must be the same as the first ordinary homology, of course, of S1 wedge S1. That's Z plus Z. And so now you see that's kind of nice because one of these Z's corresponds to the longitude, but one of these is generated by the longitude here, and the meridian is also not homologous to 0. That's the other Z. And they are perfectly dual to each other. And that's that theorem, right? That there is a non-degenerate pairing. You see it happening here in this example. There's a perfectly good geometric duality between these cycles, but somehow intersection homology doesn't see any of this, right? It just says 0. So sometimes this theory sees more than intersection homology, and the way you can view it is that these theories taken together give a more complete picture of the topology and the Poincare duality present in a singular space, as opposed to looking at one of these 2 theories alone. So one should look maybe at both of them, at the pair of these theories, IH and HI, to get a more complete understanding of the topology of a singular space. And I'll give more evidence and support for this later on, in particular in terms of, in the context of mirror symmetry. Maybe I'll also say something about some relations to physics. Intersection homology is sort of related to certain D-branes in type 2A string theory, and this theory is related to D-branes, massless D-branes arising in type 2B string theory. So maybe I'll say a word about this next time. So I think I'll stop here. Thank you. Other questions? Yes?
You just mentioned the word scattering matrix.
Yeah.
Is this related somehow to scattering in physics? Are there some
This I do not know. I mean, a scattering metric is like, if you view the standard metric on Rn, right, but you go outwards and you imagine the cone point sitting at infinity, that's sort of the scattering metric, if you reparameterize like this. So, so you in the cone, rather than going into the cone point, the scattering metric makes you fly out, this seems to capture fairly well the behavior of that theory. And so, especially the relation to mirror symmetry is, if on the one hand you relate IH and HI to mirror symmetry, but if on the other hand you succeed in expressing both theories as L2 cohomology theories, I wonder whether the two types of metric that occur there also have a significance in string theory, right? If one puts all of this together, it seems to me that there's something interesting going on, something very fascinating, but it's not completely understood yet, and a lot of research is done on that front. So, yeah.
So the intersection pairing on homology theory on the space, does it come from the structure on the spaces? So we have kind of the pairing on the spaces on the IPX?
That is a very good question, but I don't see this directly. I mean, it's a very good question whether, with respect to Spanier-Whitehead duality, for example, whether this comes from a sort of a Spanier-Whitehead type duality and is induced by that on the group level. We don't really see that yet. I mean, we've thought about it. It's not clear that this is so. It doesn't actually seem to be the case. Although it's natural to believe this at first, it doesn't actually seem to be the case, I think. Okay. Further questions?